In this session, we will be focusing on Markov chains, a special set of stochastic processes which operate in discrete time as well as discrete state space. Both of them are discrete with respect to this Markov chains, right? So wherever we have applications which are measuring the values of a particular variable, right? Values of a variable at specific predefined points in time, let's say on a monthly basis, on a yearly basis kind of stuff, at predefined points in time, and the variable values also are more and more of a discrete set. Let's say the few states are possible, jumping from one state to another state at the end of the period. So typically what we would be seeing is, in these examples, like in the insurance industry, we may see a no claim bonus system. In the HR world, we may see a performance appraisal system, or probably in the banking world or in the risk management world, we may look at a credit rating system. All these things, they can very well be modeled as Markov chains, because they operate in discrete state as well as discrete time space, and along with that they satisfy a Markovian property. What is this Markovian property? The probability of transition from state I to state J is dependent only on the state, or probably whatever is the probability of transition from state I to state J at time t, should be dependent only on the previous state, not all the earlier states, right? So it's as good as saying, okay, what is the probability of xt is equal to some state j given xt minus 1 equal to j1, xt minus 2 equal to j2, so on. All we are saying is this should be simplified as the probability of xt equal to j given xt minus 1 equal to j1, only this much. So which means the information that is pertaining to time periods t minus 2, t minus 3 and all should not be applicable. Only then we call that kind of a process as a Markovian process. And if that Markovian process is more applicable to discrete time as well as discrete state space, we call those kind of items as Markov chains. So in any Markov chain, probably the first thing that is important for us is find out the transition probabilities, means from state I to state J, right? When I talk about the words here, some of the terms are very much important for us. So when I look at a word transition probability, so moving from state I to state J, what is the probability? So when I am representing Pij, it is the probability of moving from state I to state J, and here generally we may denote it as Mn, means from time M to time N. So it's as good as writing probability of xn equal to j given xm equal to I. what is the probability associated with this? So, but in general, what we look at it is this is an n minus m step transition matrix. So, for each step Pij, this is called as one step transition matrix, means one time period, within one time period, what is the chance of moving from state I to state J? So it's as good as saying, okay, a particular company today is operating at AAA credit rating. So what is the probability that within 1 year, a company which is operating at AAA level will go to AA level? So this is what is called as one step probability. Similarly, when I say two step, within 2 years or within two periods, what is the chance that a firm that is currently at AAA rating may go to AA rating within two periods? So this is called as two step probability, two step transition. So whenever I am talking about end stage transition matrix, it is nothing but within n time periods, what is the chance that an entity which is currently in state I moves to state J. So here, under this scenario, we talk about a set of equations, how we solve those kind of transition probabilities. This transition probabilities can be solved using Chapman-Kolmogorov equations. This can be solved using Chapman-Kolmogorov equations. All we are talking about them is the probability of going from state I to state J at any point in time is same as probability of going from state I to state K and again from K to J. And this is all case. For all case, we are talking about going from state I to state K multiplied by state K to state J, and of course within that time interval itself. So M to L and L to N. So intermediately, probably it's as good as writing, okay, if I'm talking about within 2 years going to state J from state I. It means, okay, within 1 year from I to K and probably from K to J plus, okay, within 1 year going from KI to L and L to J plus probability within 1 year going from I to X multiplied by X to J. All these, the summation of all these things is what we talk about the probability of going from I to J within a 2 year period. So this kind of an equation, one thing which we have to be clear with, this kind of an equation is what we call as a Chapman-Kolmogorov equation, wherein we are looking at going from I to J is nothing but a summation over going from I to K and then from K to J within that specific time period. Now, whenever we are looking at computing or evaluating a Markov chain, two things which we look out for whenever we are evaluating a Markov chain, two things that we are primarily looking out for is one step transition probabilities from I to J. We talk about one step, we require one step transition probabilities Pij. So for all i's, it's kind of a matrix. For all i's and all j's. So these are the different i's. These are the different j's. what is the probability of going from state I to state j within one period? This is the one step transition probability, and at the same time I also require what is the initial state. Initial state, what are we talking about? And what are the one step transition probabilities? So based on this we can solve either what are the long run probabilities, right? Or we can talk about what is the probability of being in state K after let's say 5 years, provided it is in state I currently. It's as good as saying what is the probability that the firm will default within 5 years, provided it is in a very strong financial position now. These are the various calculations that could be done, or probably a person who is the safe driver today, who is getting a 60% discount on the insurance premium today. What is the chance that he will not get any discount, let's say after 5 years? So all these things can very well be computed, because the current state is a person is getting 60% discount, and we know 1 year transition probabilities are like this. So if I do this exercise 5 times, probably after 5 years, what is the kind of the situation can very well be computed. So here we actually talk about time homogeneous, versus heterogeneous or inhomogeneous. What are we saying here? When I say time homogeneous, see, we have been talking about Pij, probability of moving to state J from state I within 1 year. Now, if this within 1 year is dependent on the current time, if this within 1 year is dependent on current time, which means, okay, for a 5 years experienced company, probability of going from AAA rating to default, let's say, is 5%. But if the company is a 20-year experienced company, the probability of going from a AAA rating to a default is only 2%. If I have such kind of a mechanism, that Pij is differing for different time periods, right? Okay, depending on if it is existing for last 20 years versus if it is existing for last 5 years, probably the 1 year transition probabilities are changing. Those are what are called as time inhomogeneous. They are not uniform across the time. Means the probability of going from AAA rating to default changes. Though it's a 1 year probability, we are saying it changes from year 3 to year 4 versus year 10 to year 11. If that is what we are trying to consider, and we are not taking it uniformly, if we are talking about time homogeneous, whether we are talking of moving from 3 to 4, if from year 3 to year 4, going from I to J is same as going from I to J between year 10 and year 11, or it's even same as going from I to J between year 100 and year 101, because the probability is only based on the difference. So it's not based on the current time. Whereas when we talk about time inhomogeneous kind of processes, The dependency is on the current time also, not just the difference between the times. So that becomes a time inhomogeneous Markov chain. For some applications, it is very much required that we go for a time inhomogeneous Markov chain, whereas for a time homogeneous one, obviously I don't need to bother about this, because all I need is it a one step or a two step or a three step. So we for those kind of stuff, if I just have one step transition probabilities, if I have one step transition probability matrix, which is an n by n kind of matrix, where n is talking about the number of states, where n by n matrix is there, that is a one step transition probability matrix, which can, and along with the help of the initial state, it can actually help me to compute the probabilities after any number of periods. And let me tell you, as a part of this one step transition probability matrix, every row every row, the summation of every row value should be equal to 1, because all we are talking of is from this particular state, I am trying to find out all the probable states that it can go into. Like a company which is having a AAA rating, there is a some chance that it will go to AA, there is some chance that it will go to B, there is some chance that it will go to C, and there is some chance that it will default within the next 1 year. Now, when I add up all these probabilities, it should be equal to 1. The same way, a AA rated firm, there is some chance that it will go to AAA, there is some chance that it will go to B. Again, when I add up all these numbers, it should be equal to 1 itself. So the total of all the rows individually, in case of this one step transition probability matrix, the sum of all the rows individually should be equal to 1, right? And obviously it also requires, once I know, okay, currently my particular, okay, there are 4 states, currently I am in state 3, and this is a 4 by 4 matrix, which is the probabilities from state A, B, C, D to state A, B, C, D. Let's say these are A, B, C, D. So currently I am in state C, and I want to find out, and I know that these are the transition probabilities, wherein each period the summation should be equal to 1. Now when I do this multiplication, which means this is a one step transition probability. So if this is in period 0, probably after multiplication, whatever the set of values I am getting, this is after 1 year. Now this again, if I multiply it with this transition matrix, I'll get the values at the end of 2 years. Like that, after n periods, whatever are the values that are present, that is going to be the probability that a process that is starting in state C, after right now, after n years, it will land up into state A or state B or state C kind of example. So in general, the credit rating systems, the typical no claim bonus systems of the insurance companies, they all typically can be classified as a Markov chains, especially the discount that needs to be given for a driver who has not committed any accident in the current year, or depending on what his current state is, what level of discount he is in, he would be either added 10% or removed 10% kind of positions. So different states will be created, either he would be jumping to a higher state or he would be falling to a lower state, depending on the accident made during this particular period or not made during this particular period. And as long as the dependency is on just the last period alone. It's a perfect Markov process, right? Probably the current rating is dependent purely on the last year's rating. If the current year's rating is purely dependent on the last year's rating and the transition probability matrix, only two inputs are going, the last year's rating and the current transition probability matrix. Using these two, if I am trying to decide the rating for this year, it's a perfect Markovian and Markovian time independent kind of a process. Time homogeneous kind of a process. But in some cases, what could very well happen is a rating agency may see not just last 1 year, but let's say the last 2 year rating also. So depending on a year before that also, whatever was the rating assigned to him, based on that it can take a call. Okay, in the last 2 years, if he has not committed, if there was consistency in the financial performance, then let's upgrade the rating. But only if it is 1 year of better performance, let's not upgrade the rating. So when such kind of things are there, it is becoming a little bit, it's not a pure Markov kind of a process. So what we could very well do is, we will try to split it. Right, I'll show that in one of the numericals when we deal with it, but we'll try to split it. Like, okay, we are talking about 1 year, 1 year no accident, no accident in the previous year also, 1 year no accident, but accident in the previous year. So these two will go as two different states. Though we are talking about no accident state, but we are talking about if the accident was not there in the year before that, we are grouping it into one category, or if it is if the accident was there in the year previous to that, we are grouping into another category. And along with that, as I am saying, even a time inhomogeneous kind of processes also come up sometimes, right? If at all there is some kind of a differentiation being brought out, right? Like probably a highly experienced companies, we have, let's say, a different transition probability matrix, versus new companies, we have a different transition probability matrix. So whenever we are talking about such a kind, depending on the year of operation, though we are talking about year of time to default, with the probability of default within 1 year, if I say no, it is dependent on how long the company is operating also. Probably for a 2-year-old company, the probability of default within 1 year from AAA rating is very high. Compared to a well-experienced company, the probability of default from a very highly rated kind of a state might be much lesser. In those cases, it is advised to go for modeling it as time inhomogeneous kind of a process. Right? Now, if I look at a few more aspects, simple random walk, some kind of Markovian processes. If I am talking about a simple random walk kind of a process, where we have defined yn is nothing but x1 plus x2 plus so on up to xn, and of course the probability of yn equal to 1 and yn equal to -1, it's going with p and 1 minus p kind of scenario. We called this as a simple random walk kind of a scenario. And because the increments are independent, whenever increments are independent, we said that this particular process is Markovian. So a regular simple random walk or symmetric kind of a random walk, all these things typically fall under the Markovian kind of a processes itself. Now, this is where I have an important point to talk about. Let's say we talk about two states A and B, right? We talk about two states A and B. Now let's say a process has come from state A to state B and immediately it is going away from state B to state A. Now, if at all the probability of x n plus 1 is state A, given in xn it is in state B. So which means in the next transition it goes to state A from state B, means it will not be retained in state B at all. If it is compulsory, then we say the B is this particular process is having a reflecting boundary. So here some of the words: reflecting boundary at B. The moment it comes to B, within the next period itself it will go back to A, and that is for sure. Then we call it as reflecting boundary. But in case, okay, the moment it comes to B, it will be there in B only, it does not go back to A. Then B is said to be absorbing boundary. So in that case what happens is the probability of xn plus 1 equal to B given xn equal to B is 1, because it will not go anywhere else. It will be there in that particular state only. In that case, we call that particular process to have an absorbing boundary at B. But if both of them are there, means there is some chance that it can go back to A. So probably here P of x n plus 1 is equal to B given P of xn equal to B, or P of xn plus 1 equal to A given xn equal to B. So probably this might be with some probability T, and this might be with some probability 1 minus T, which means there is a chance that it can reflect and there is a chance that it can absorb. In those cases, we say that the boundary is a mixed kind of a boundary. So if it can go back to the next state, we say it is reflecting boundary. If it definitely stays in the same state itself, we call it as an absorbing boundary. But if it has either of the scenarios possible, either it can reflect or it can absorb, then we call it as a mixed boundary, right? So this is one concept that we need to be comfortable with. Then the most important piece in this Markovian chains is the stationary distribution. Checking whether this Markovian chain is stationary or not. So as we said, for a Markovian chain, the input that I require is the initial state as well as the transition probability. The initial stage, transition probability, a matrix multiplication of the two will give me the resulting state. Now, if I am saying using this multiplication, right, probably I look at it like this. This is pi I initial and transition probability going with ij. A multiplication of it is giving me the state, the position at some other, the next time period. Now, if at all we are able to equate these two states, wherein all these are always positive or zero at the worst. So each of these items, each of these probabilities, because these are, the initial state is nothing but initial probabilities, multiply with the transition probabilities. So even these things should be probabilities, and the summation of them at any point in time should be equal to 1. So that's where if we have to really write the rules about a stationary distribution, what we simply say is the pi j is equal to pi I multiplied by pij for all values of I, and pi j for each of the values should be greater than or equal to 0, and the summation of all pi j's should be equal to 1. So what it means is, in the long run, if this distribution is more and more stationary, or at any point after n steps, if my process reaches this, state, it will be there only forever. And this is the long run stage of this particular process. In the long run, the probability is that it will be in the state A, B, C, D are going to be these kind of probabilities. That is what we talk about a particular Markov chain being stationary. So apart from the stationary, for a Markov chain, we also talk about a few more characteristics. One is to do with irreducibility. Whenever we say Markov chain is irreducible, see, from every state, let's say we are talking about 4 states. From every state, in some form or the other, every other state should be accessible. Right? Probably here, if I am talking about these as state A, B, C, D, probably, yeah, if I am looking at state D, it is approached from A. It is approachable from B via C and D. It's not directly approachable. No need to be directly approachable. But it has to be approachable. So from B you can reach D. From C you can reach D. Similarly, you look at A. From B you can come to C and then A. But again, from C you can reach A. But from D there is no way you can reach A. In this case, it is, I cannot say that this is irreducible, because there is no way of going back from D to A. So probably it's like probability dA is 0 even after 1 period or 2 periods, 3 step, 4 step, anything. There is no way you can reach A in this kind of a process. So this is what will be one of the properties, right? When I am looking at a Markov chain, I have to check for the irreducibility behavior. Any state should be reached from any other state, whether it is after one transition or two transitions. Means even if there is a long route, if there is a route, then we can say that it is irreducible. Otherwise, it is a reducible kind of a transition matrix itself, right? That is one thing we have to be comfortable with. Then whenever we are talking about a stationarity, right, probably if the question is about find the stationary distribution, So all I should look out for is, okay, start with pi 1, pi 2, pi 3, pi 4 being the initial probabilities. Then you take the transition P11, P12, P13, P14, P21, P22, P23, P24, P31, P32, P33, P34, and P41, P42, P43, P44. Now from here I multiply these two and I will again equate it to pi 1, pi 2, pi 3, pi 4. So from here I can very well do the simplification like pi 1 p11 plus pi 2 p21 pi 3 p31 pi 4 p41 equal to pi 1. So like that I can have a set of equations, and when I am solving for the equations, whatever the pi 1, pi 2, pi 3, pi 4, because the summation, again one more rule is pi 1 plus pi 2 plus pi 3 plus pi 4 should be equal to 1. So when I am doing these kind of simplifications and trying to find out pi 1, pi 2, pi 3, pi 4, whatever those numbers work out, we call that to be the stationary distribution. We'll take up a numerical regarding finding the stationary distribution of a Markov chain, and based on that we can do the calculations and get a clarity from. Now here one more concept that needs to be understood very well is the concept of periodicity. Periodicity is nothing but the minimum time or minimum steps to reach a particular state from other state. Minimum number of steps to reach a particular state from the other state, especially if that is greater than 1, right? If that is greater than 1, we say that that particular process is periodic. For example, I'm talking about a state A and a state B. So within one period, let's say something is coming from state A to state B, and in the next period it comes to state A again. Means a process in state A to come back to state A again, it requires 2 periods, because in one period it will definitely go to state B and then it can come down to state A. Similarly from B, if it is currently in B, it takes 2 periods to again come back to B. So A requires 2 periods, B requires 2 periods, which means the minimum period for anything to be reached is 2. So in this case we say that the periodicity for this kind of a process is 2. So the minimum possible number of steps to reach one state back again from the same state, the minimum number of steps to reach that state from that same state is what we are calling it as a periodicity. So the returning will, or in the other case, let's say I have a diagram like this, state A, state B. From state A it comes to B, but here I have a mixed process where it can either stay in B or it can come to A. So there is a possibility that if it is in state A, to come back to A, it may take either 2, 3, 4, any number of steps. 2 means it comes here, it comes back. 3 means it comes here, it can stay here for one more period and then come back. 2, 3, 4, any number of steps can happen. So what is that common multiple that is associated here? 1. So when the common multiple is 1, we say that that particular process is a periodic. that Markov chain is aperiodic, especially if the greatest common divisor of all the number of steps, the greatest common divisor of all the number of steps that can be reached, if it is equal to 1, then we say it is aperiodic, right? Generally, if that particular chain, again one more relationship, if it is irreducible, if this particular chain is irreducible, then the period is same across. If the chain is irreducible, then the period is same. So I don't need to check for B, C, D again. If every state can be reached from every other state, we say that it is irreducible. And if it is irreducible, then the period is going to be the same across for all of them. So for the entire chain, the period is going to be the same itself. If one of them is aperiodic, then the entire chain will be aperiodic itself. So wherever the periodicity is equal to 1, and if it is not periodic, we say that it is aperiodic. So in general, because in a Markov chain, if every state is going to be aperiodic, we say that the whole chain itself is aperiodic. Because if one of them is aperiodic, and if the process is irreducible, then I can very well say that all of them will have the same period, means all of them will have a period of 1, all of them are aperiodic, which means overall it is boiling down to the whole Markov chain itself is aperiodic itself. Now, coming back to the stationary distribution, there are a few important rules for us to remember regarding the stationary distribution. If you find a particular Markov chain, number of states are finite. If you find that the number of states are finite, you will find at least one stationary distribution. You may find more also, but at least one stationary distribution will be there. But if along with the number of states being finite, along with that, if every state can be reachable from every other state also, not just the finite number of states, but if it is irreducible also, every state can be reached from every other state, then we are talking about not at least one, it's only one stationary distribution that is available. Right? So, if the number of states are finite, you will find at least one stationary distribution, but along with the finite number of states, if the Markov chain is irreducible, means every element is reachable from every other element, every state is reachable from every other state, then it is going to have on a unique stationary distribution only. And along with being irreducible, even if it is aperiodic, means periodicity is equal to 1, we can very well say that in the long run, the process will come towards this stationary distribution itself. If it is even aperiodic, means periodicity is 1, we can say that in the long run, the process will conform to this distribution itself. So these are the reasons why we look at the number of states, the irreducibility in the behavior, and the aperiodic nature in the station in the Markovian chain, so that we can really make some kind of conclusions whether the what are the long term probabilities. Probably if a process is starting in state I now, what are the probabilities that it will go into state J, K, L, M, probably after in the long run. It could be 5 years, 10 years, but the moment it is approaching, see, what you see is the process will keep approaching towards that long run stationary distribution. The moment it comes it comes equal to that long run stationary distribution, after that subsequent periods of time, the process will keep continuing in that states with that kind of probabilities only, right? So generally whenever we are trying to find out, right, now comes the bigger problem in terms of how do I find PIJs, right? The actual thing that comes, how do we find PIJs so that they can be used for the finding out the stationary distributions and all that. So in the historical data, I'll typically see, okay, number of observations which are belonging, number of observations, or probably if you say number of companies, okay, probably if I say probability of moving from AAA rating to a AA rating within 1 year. Now I will take the number of companies with a AA rating. Then I will also take the number of companies within the last 1 year which were rated AAA, number of them which became AA. So this will give me the number for PIJ. So now similarly, number of AAA rated companies which have stayed in AAA itself in this year also. Even this, if I am taking the division, probably this I will get PII. So PII, PIJ, these kind of when I try to find out this kind of probabilities, and then assign the transition matrix. So going from one state to another, if I have to assign the probabilities, it is nothing but from the historical data, I'll try to look out for number of companies or number of observations which are in the state I in the previous period, but this period they have moved to state J. So this the division of Nij by Ni is going to give me Pij, which is going to give me a transition probability kind of a matrix. And on this transition probability matrix, we are to test out statistically, we are going to perform a chi-square test to look out for it for the consistency. So we are talking about 3 consecutive observations, probably the 3 years or 3 consecutive kind of observations of the same process. We are looking at whether the 2 years back data is having any kind of influence on the current. So that is what is to test out the Markovian property. So here we are making a kind of a null hypothesis saying that the process exhibits Markovian kind of a property, whereas the alternate hypothesis goes with the process does not exhibit Markovian. So the chi-square test, whatever we are using to test out the same, is nothing but, okay, we are talking about the number of firms Nijk. So Ijk is given in the given data set. We are talking about moving from state I to state J and then to K, where we are looking at, right, where we are looking at typically Nijk minus Nij. Let me write down the formula, then I will explain the logic behind it. into pjk squared divided by nij into pjk. Especially when we talk about chi-square test, the chi-square test generally we perform it as the summation of observed minus expected squared by expected. Now here what is that we are saying? The expected is nij multiplied by pjk. Nij is nothing but summation of all the states nijk, the triple within the 3 period, 3 consecutive observations from I to j. So something being in the state I in the first period, moving to j in the next, and then to the k. So nijk over all the k's. I am trying to find out nij through this, and this multiplied by pkj, which is nothing but njk divided by nj, which is nothing but we have found out through this kind of a mechanism. So this is the chi-square test that we are typically using, and obviously if the significance level for it is less than the 0.05, we reject the null hypothesis and go with the alternative and say that this process does not exhibit a Markovian kind of a property. Otherwise, we don't have any evidence to reject the null hypothesis. So, just to summarize the conceptual part of it, a Markov chain is primarily associated with discrete time, discrete state kind of a process, a stochastic process, which will exhibit Markovian kind of a property, and it could be associated. I mean, as far as they are concerned, we are looking at the transition probabilities, and using the initial state, we can even find out the stationary distributions associated with the Markov chain. We can even test out whether the chain is irreducible or aperiodic, and whether it will conform to the long run stationary distribution or not. And we can even find out what is the probability that it would be in state j given after n periods, given that it is in state I currently. And we can also check out for in what cases the stationary distribution can come out, unique stationary distribution, or at least one stationary distribution. So what kind of processes result into what kind of stationary distribution? All these things can quite comfortably be evaluated, and the decisions regarding the long run probabilities and long run behavior of a particular process can very well be predicted, provided it follows a Markov kind of a chain process. So what we will do now is regarding these various aspects, we'll take up a few numericals, try to work out the numericals so that we could relate all these concepts quite comfortably to the practical world. Alright, so let's move forward with the numericals regarding the same.